From a Badlands dark site, good evening. I'm Richard Walker. On the virtual star party tonight, the Western Veil Nebula, NGC 6960, the aftermath of a massive supernova more than 10,000 years ago. A supernova from a star 20 times more massive than our Sun. Then, in the constellation Cygnus, 1,800 light years from planet Earth, the Pelican Nebula, an active mix of star formation and evolving gas clouds where the light from young energetic stars are transforming cold gas to hot, causing an ionization front to advance outward at tremendous speed. Plus, NGC 7078 M15, a unique globular cluster in the constellation Pegasus. At 12 billion years old, it is one of the oldest globular clusters known, home to over 100,000 stars and the first planetary nebula discovered within a globular cluster in the year 1928. All that and more on tonight's virtual tour at this amazing dark site. Strap yourselves in. So let's begin by taking a closer look at the telescope that's going to take us to the far reaches of the Milky Way galaxy. We still got a little bit of time left before it gets dark, so this will be a good opportunity to show you these features. First off, this is a refractor, a 6-inch 152 millimeters. It's a short focal length telescope. Over here is a longer focal length telescope. This telescope is f11. Whereas that one is 5.9. Now there's something to know about focal lengths. This is also 102 millimeters. It's a little smaller. Now the difference between these two telescopes, besides the aperture, is the speed. And believe it or not, the speed of a telescope, whether it's slow, meaning a long focal length telescope like f11, like this one, or fast, an f5.9, like the larger one, the 6-inch. The difference is in magnification. If you were to take a 10 millimeter eyepiece and put it in a 1,000 millimeter focal length telescope, it would yield roughly about 100 power. You take the same eyepiece and you put it in a 500 millimeter telescope and it'll give you 50 power. Magnification equals telescope focal length divided by the focal length of the eyepiece. So with a long focal length telescope, you're going to get a lot more power out of any given eyepiece than you would do with a shorter one. But there's trade-offs between a long focal length telescope and a short focal length telescope. And the trade-offs are, this has a narrow field of view, the long focal length telescope. Due to the power, you're closer on the object. As you get closer to the object, you cut out the surrounding star field. Whereas for rich field viewing, is what they call a short focal length telescope, like this one, you get a much bigger field of view in the eyepiece and a lot more light as a result, so it's faster. There's another advantage and disadvantage to both of these. If you want to do planetary and lunar viewing, you're much better off with the long focal length telescope rather than the short, and the smaller aperture. And the reason is, views of planets and the moon require high power, and the larger the aperture, the more it is affected to atmospheric turbulence, or what is known in astronomical terms, the seeing. Now here in South Dakota, we reside pretty much underneath the jet stream. It's the reason why our weather changes just on a dime. As the turbulence in the atmosphere increases, it's like looking through the bottom of a swimming pool, and the image is very wavy. Now at high power, that distortion is magnified. So if you're looking through a 6-inch telescope, then you're looking through a 6-inch column of air, more affected by the seeing. Whereas a 102 millimeter telescope looks through a smaller column of air, and therefore it is less affected by the seeing. So if nebulosity is your cup of tea, then you really want a fast scope and large aperture. Outside of planetary nebulae, most nebulous targets are very big. They are low contrast, so you want to get as much light as you can into your optics, and that means a fast scope with large aperture. But, like I said, if you want to specialize in the moon and the planets, then a long focal length telescope is the way to go. The other factor to consider when choosing a long focal length versus a short focal length telescope is that when light passes through a prism, as you know, it scatters, and when light passes through glass, it scatters. Now, when you have a short focal length telescope, the angle of attack, you might call it, is very steep, or the light cone is very steep, like that. So when it comes into the eyepiece, it's scattered. It doesn't have time to line up. And that's why back in the day, most of the telescopes you saw were very long focal length, f/15 and longer. And the reason why they did that was in order to let the light come back into focus. During William Herschel's time in the 1700s, they had extremely long focal length telescopes. And the reason is, the optics they had, they didn't have the fluoride and the FP53 lens elements that we have today. Now today there are what they call ED refractors. And what it is, it's a low depression glass that's put in the second part of the lens element. And that helps correct the light, but not fully. To get a really nice corrected light, you need what they call a triplet. It has 3 different lenses in it. Now this chromatic aberration is more apparent at high power and on bright objects. So if you're doing nebulosity, you probably wouldn't notice it all that much if you had a halfway decent refractor. Now there's some real cheapos out there that when you look through them, it's like the Jimi Hendrix Purple Haze experience, and psychedelic all over the place. Those you want to avoid because they compromise the image and you're unable to really discern finer detail. So once again, short focal length telescopes are more difficult to correct. If you're getting one, you want to get one at least that's an ED, a doublet that has an ED element in it. And if you get a longer focal length telescope, then you're able to get by with a little bit less correction as far as the lens is concerned, because the physical length of the scope will help correct some of that. What we have here from Telescope Service is an F11. Now this is an ED. There is a low depression glass element in here. It's a doublet, not a triplet, but because of that long focal length, any chromatic aberration that's in there is reduced greatly. Not totally eliminated, but really put pretty far down. And the price of this is very reasonable. And so that is why it's best to stick with the longer focal length telescopes for the planets and the moon, because then those targets tend to be kind of bright. And if you have a refractor that's not up to the task, you're going to see a lot of halos and purple haze, and it's going to really disappoint you for sure. And you're going to miss out on some of the finer details, the bands of Jupiter, the Cassini division, and Saturn and such. Okay, so tonight what we're going to be using is night vision. Now, night vision is a military PVS-14 monocular that's used for night ops. But we're going to be connecting it to a 55mm Plössl in order to accelerate the dim lights from nebulosity. Works really good, and it will increase your aperture yield quite a bit to where we can actually photograph these things afocally. So I'm going to be showing you images that were photographed afocally through the PVS-14 connected to the 55mm Plössl, and that inserted into the 2-inch star diagonal. Now, what do I mean by afocal? Afocal photography is simply taking a camera, and this is a Canon G12. They don't make them anymore, but it works pretty well for this kind of technique. And putting up to the eyepiece like that, some people use an iPhone or a phone, and then taking an exposure. It's not really astrophotography, but it's fun, and it's quick, and it's easy. And if you're using a PVS-14 accelerating that light, you can image the nebulous targets. Now, the goal tonight is not going to be creating a highly detailed image using this afocal system, but to convey the visual experience using a PVS-14 night vision monocular. And I'll be showing those images first, and followed by narrowband images that were taken here and elsewhere around this area to show you what it looks like when you accumulate large amounts of data, which is probably what most people are used to seeing when they go online. Well, all right, when we return, we're going to climb aboard this 152 here and head on out to the constellation Cygnus and the Western Veil Nebula, NGC 6960. See you after sundown. Okay, I'm going to do a little observing and a little explaining. Let's go to the veil, NGC 6960, the Western Veil to be precise. So we'll dial that into this hand controller. Makes it almost too easy, I'll tell you. 6960, enter. It should be right about up in there. Yeah, I can see Cygnus now. I can see Denham, the Swan. There it goes. Pretty high up, which is good. That's a good thing. It gets us nice and less atmosphere, so you'll see it better. Okay, so here we are, a summertime favorite, the Western Veil Nebula, NGC 6960. Now, it's what's left over from a supermassive nova more than 10,000 years ago, and the star was 20 times more massive than our sun. Now, the remnants of this colossal blast have since expanded to cover an area of the sky roughly 3 degrees in diameter, which includes Fleming's Triangular Wisp and the Eastern Veil Nebula. Now, here I've got a narrowband
image capture showing the double iodized oxygen wavelength visible in the blue gas-like flame floating above the veil and below the dominant star 52 Cygni. This image represents just under 13 hours of data collected. So like I had said earlier, these narrowband images really require a lot of time, patience, and skill.
Okay, so next we're going to go to Fleming's Triangular Wisp, and that's real close to NGC 6960. So basically, there's no designation, so basically we'll just bump the scope here a little bit. You know, let's see, no, go the other way. Okay, there you are. Okay, all right, there it is. Check it out.
So here we have Fleming's Triangular Wisp. Now it's a wispy area of the Veil Nebula discovered by Wilhelmina Fleming in 1904 while examining photographic plates at the Harvard Observatory. But as was the custom of those days, the credit for the discovery went to the researcher's superior, and in this case, it was Professor Edward Charles Pickering, director of the observatory. Hence, the more official name is Pickering's Triangle. But that didn't discourage Wilhelmina Fleming. Now here it is in narrowband. During her career, she helped develop a common designation system for stars, cataloging thousands of them, along with other astronomical phenomenon. Among several career achievements that advanced astronomy, Fleming is also noted for her discovery of the famous Horsehead Nebula in the constellation Orion in 1888. Not bad for a single mom who started out as a maid in the home of Professor Pickering.
Okay, also in Cygnus is the Pelican Nebula IC 5070, and we have an IC catalog here, I believe. See, NGC, there it is. IC 5070. Enter. So here we go. It's going to do a complete loop around because it has to get orientated in a way that allows it to get on the target. Cygnus is just at zenith, almost like right up above there. And this target is in Denham, which I can see right here. So it's going to be pointing right about in that area there. That's where Denham is right now. I can see it. Pretty amazing piece of equipment, I'll tell you. And the fact that it can handle two scopes simultaneously is just way cool. All right, here we are. So, yeah, man, I'll tell you. Oh, yeah. Here it is, man.
Now it's nearby the first magnitude star Denham, the tail of the swan, and is divided from its more predominant neighbor, the North American Nebula, by a molecular cloud filled with dark dust. And here we have the Pelican in narrowband. 15 hours of data captured at a focal length of 404 millimeters. So you can see how that short focal length really grabs a lot of the sky and gives you a really nice feel of how extensive some of these nebulous targets are. Now the Pelican is much studied because it has a particularly active mix of star formation and evolving gas clouds. The light from these young agenic stars is slowly transforming cold gas to hot, causing an ionization front to advance outward. Millions of years from now, this nebula might no longer be known as the Pelican, as the balance of placement of stars and gas will leave something that appears completely different. Now you can see here in the image the ionization front advancing outward. It forms the neck and the lower body of the Pelican. Now there are a number of unusually dense filaments of cold gas that are still visible along the ionization front. Among them are the jets emitting from Herbig-Haro object 555, indicated by the red arrow. Now here's HH 555 imaged at a focal length of 3,900 millimeters, representing 2 hours and 15 minutes of data collected. Herbig-Haro objects are jets of matter, and particularly iodized gas ejected by newborn stars, which appear as patches of nebulosity in star-forming regions. These jets are ejected at speeds of several hundred kilometers per second and collide with nearby dust and gas, producing these dramatic shock fronts that glow as a result of gas being heated as it collides with the interstellar medium. Now, these jets are eventually blown away by the wind produced by the young star and disappear over time, about a few 100,000 years at most. HH 555 is the most predominant example of this kind of object found in the Pelican Nebula.
Okay, we're on M15, and I'm going to try to do a little afocal here with this night vision. We'll do a 1 second exposure at f2.8. That's the fastest this will go. Cool. Yeah. Not bad for a 1 second exposure. Check it out.
M15 is one of the most amazing star clusters out there. That out there is 33,600 light years from Earth. You wouldn't know it to look at it through a telescope, but it's 175 light years across. Now, when you compare that to our solar system, which is just 11 and a half days across, and you get a better idea on how big M15 really is. Now, here's a monochrome capture, one of the first I did of a globular of M15. Along with the first planetary nebula discovered within a globular cluster, M15 is noted for containing a large number of variable stars and pulsars, including one double neutron star system and two bright X-ray sources. Now, this Hubble capture shows much more detail and resolves many more stars, and gives you a better appreciation on how beautiful this cluster really is. Now, M15 you could see with the naked eye under good conditions and can be observed with binoculars or small telescopes, appearing as like a fuzzy star. But you really need a telescope of 6 inches to begin to resolve individual stars.
Okay, so let's take a trip to the constellation Serpens, the Serpent, and the Eagle Nebula. And that should be kind of like down that way. Yeah, the meridian would be right about there. When an object is on the meridian, it's at the highest point that it'll be in the sky. Pretty much on the meridian, really, because I'm standing in the north, and so that is south right there, and that's the meridian. Now, from what I could see, Jupiter and Saturn haven't reached the meridian yet, so they still got a little higher to go. And the higher an object is, the better off you are, because you're looking through less atmosphere, so things look pretty good. Oh yeah, I could see it. Wow, awesome, just right there.
Okay, so here it is in night vision. And we've got the whole nebula there. It's rather large, and if you concentrate, you could pick out the most famous part of the nebula, the Pillars of Creation. Now, it's part of an active star-forming region composed of cosmic dust and gas that hide newborn stars within the wispy columns. Now, here we have the Eagle imaged at a focal length of 404 millimeters, and that's the advantage of the short focal length telescope. You could really get a sense on how extensive these objects are. And now here it's imaged at 3,900 millimeters. Now, the difference in detail is quite obvious. You can see the pillars much better, but what's not obvious is the significant degree of difficulty in imaging at the longer focal lengths. It took me quite a few years to be able to proficiently image at that focal length. But once you get there, it opens up a whole new area of targets. As a matter of fact, you could go back to targets that you had imaged before and image them at 3,900, and it totally changes the perspective of it. Now, stretching roughly 4 to 5 light years, the Pillars of Creation, shown here in this famous Hubble image, are a fascinating but relatively small feature of the entire Eagle Nebula, which is approximately 70 by 55 light years. This night sky wonder is located 7,000 light years from Earth and is best viewed during July.
All right, well, let's move on to the Dumbbell Nebula in the constellation Vulpecula, the Fox. And that would be in Charlie's catalog, M27, Charles Messier, that is. And M27, let the magic begin. Okay, M27, let's see how accurate this alignment was. Bingo, right there. Wow, cool. I love it, you know. It's like, you know, it's like coming, you know, home and supper's ready, you know what I'm saying? I love it. There it is, right there. Beautiful.
The Dumbbell Nebula, also known as M27. It was the first planetary nebula ever discovered. However, the term planetary nebula is a bit of a misnomer, which was based on the nebula's round planet-like appearance when observed by astronomers through the early telescopes of the 1780s.
Ooh, look at that satellite. Oh, man. Satellite went right through it. Cool. Oh, man. Awesome. Okay.
The Dumbbell Nebula is a result of an old star that has shed its outer layers in a beautiful glowing display of color. Contrary to the writings of songwriter-singer Neil Young, planetary nebulae have more fun at burning out and fading away than the rest of us. Now, there are many examples of planetary nebulae. In fact, there is really lots and lots of them out there. A lot of them are just too faint to really do any visual work. But one of the famous planetary nebulae is the Ring Nebula in the constellation Lyra. There it is there in narrowband. But now back to M27. It resides in the constellation Vulpecula, the Fox, more than 1,200 light years away. As seen in this narrowband image captured in Rapid City at a focal length of 3,900 millimeters, M27 hosts many knots of gas and dust. Their sizes typically range from 17 billion to 56 billion kilometers, which is several times larger than the distance from the Sun to Pluto, each containing as much mass as 3 planet Earths. Pretty amazing stuff.
Well, that'll do it for this virtual star party. If you like what you're seeing here tonight, consider becoming a member.